2023 was the year of prompts, 2025 is the year of AI agents, and heading into 2026, the AI skill gap's only getting wider between professionals who use AI and those who can deploy it. Over the next 60 minutes, we'll explore the journey from LLMs to Agentic AI, broken down into 3 levels of depth. Agentic AI, tool-using AI, reactive intelligence. Hello everyone, welcome to today's session. So the agenda and the learning objectives from our session today. Number 1 is once we wrap the session up, you will have an understanding of the evolution of LLMs and the whole Gen AI revolution. And actually a lot has happened in the last 2+ years since. Next, we'll basically look at how agentic AI compares with traditional machine learning. We'll also look at the core components that make up agentic AI systems, and then we'll look at some practical design patterns, and we'll also take a look at a hands-on live demo. We're talking IK. I know we're talking about, how you can land that next opportunity. So what I actually built here is actually a simple agentic AI job finder. If you're still using old Fang Prep guides, you're already losing ground. The rules have changed, and this free AI playbook shows you what's really being tested in modern Fang interviews, insider strategies, hidden evaluation matrix, a 90-day mastery plan, the exact playbook successful candidates are using right now. Everyone's grabbing it. Don't be the one left behind. Link in description. I'll give you a quick introduction about myself. My name is Sanjay Dar. I've really spent my entire career in IT. So that's my background. Super excited to jump into the agenda that we have for you here today. So let's start with the basics. What is agentic AI? AI agents are basically autonomous software that can perceive their environment, they process information, they can take actions to achieve goals. Unlike traditional software follows predefined rules. AI agents generally leverage large language models. In terms of some of the key characteristics of agentic systems, number 1, they have to have some degree of autonomy where they have the ability to operate independently, the ability to have perception. So this is where they can gather and process information from their environment. In some cases, they also have reasoning capabilities where they can break down complex problems and plan solutions. They can also do execution in terms of being able to execute tasks, using things like tools or APIs, things that are external to the LLM. So data that the LLM may not be trained on. So if there's external data, they do have the ability to connect to some of these external sources and get the additional data they need to solve some of these problems or to achieve some of the goals that they've been given. And they also tend to be adaptive, where they do learn based on the experience and based on some of the feedback. So you can see in terms of contrasting with traditional ML, traditional ML tends to be very predictive in terms of the outputs that they generate. Agentic AI are generally working towards a goal. They're action-oriented with reasoning capabilities. Let's take a quick look at how LLMs have evolved in the last 2+ years. I clearly remember November of 2022, because this was the time I was actually at AWS and I was working with some very large global customers. And this was when ChatGPT was publicly announced. And I remember my phone ringing off the hook with, and these are some, leaders at large customers, calling and really trying to understand how they can partner with AWS at that time to solve some of their problems using generative AI. In fact, the problems were not even clearly defined at that time. So my conversation at that time was, hey, our CEOs told us we need to do something with Gen AI. We don't exactly know what. Can you help us? So I think we've come a long way from there. So if we sort of rewind the tape back to early 2023, so this is shortly after ChatGPT went live, a lot of people were tending to use some of these large language models or these generative AI tools as a microtasker. So, hey, write me an email, or write me a poem, or write me a song, and generate an image of a cat that's sitting on the moon, or a dog that is playing with a horse. So that was really where this started off, and a lot of people were really using generative AI almost like a better Google search. So instead of asking Google, searching for something on Google, clicking on maybe whatever the results it returned, reading through it and trying to understand what you were looking for, you were basically sort of asking these questions to AI. So the next phase, really moving into mid to sort of late 2023, we saw this, AI sort of moved into this co-pilot sort of mode. So this is where really people were using AI to sort of discuss ideas. So if you needed to write a document or if you needed to plan a project, you would sort of, work together and sort of get into this Q&A style, question answer style format where you would say a few things, the AI would come back and, give you some more information. They'd say, no, not this. Can you change this, or can you adjust this, or make this a higher priority, or this, allocate more time for this task. And then you would sort of, work in this co-pilot sort of mode. Looking in early 2024, we sort of saw this movement where AI was more of a delegate, where it would basically do things for you, where you could, delegate certain tasks. So if you needed to do some sort of research, you could sort of have, AI go off and run some sort of research and then come back to you with results. It could do things like it could monitor systems. It could maybe, look at system logs. It could send you a summary. It could sort of help you find and compare different types of data. If you could use it as a shopping, hey, go off and find me, what are some of the products in this category? So, and compare prices for X, Y, and Z, or compare airfares to, I want to fly to, from San Francisco to New York, and, find me some fares and give me some comparison. If you move into sort of present day, and this is also going back, maybe since the last year plus or so, this is where, when we talk about agentic AI, this is where AI is actually, people are looking at, like as a teammate. So this is where you're actually enhancing teams. And I know there's, in fact, some people, I would say some people are even pushing it, saying it will completely replace certain individuals. I still don't see that today. I still see AI as a teammate, and where AI can help increase a lot of efficiency. And depending on certain tasks, it can do those tasks autonomously. But really, this is where you could have AI do things like participate in meetings, write down a summary, send you the meeting minutes. It can actually create and even distribute institutional knowledge. So it can actually update wiki pages. It can update, let's say different SharePoint sites or document repositories. It can look for inefficiencies in different processes. And really, it can work in an enterprise level where it can actually look at data. It can give you insights from data. And it's almost like a digital employee. Yeah, so that's sort of where we stand today. And I know there's probably, there's different pundits who make different predictions, but this is sort of where we stand at today. In terms of completely replacing an individual human being, I don't see that yet today. It's something we just have to wait and watch if, where this would evolve to. So let's take a look at what are some of the different types of AI agents that are available out there. So there's really 4 sort of broad categories of types of agents. The first one being, basically a simple reactive agent. Some people also refer to this as reflex agent. So this is really the most basic type of AI agent, and is designed to operate based on direct responses to environmental conditions. So these agents follow predefined rules to make decisions, and they don't sort of consider past experience or even future consequences. So these reactive agents, they apply current perceptions of the environment based on a fixed set of rules. For example, if you look at a thermostat, it's a basic, simple reactive agent that, it'll either turn on the heating or cooling, if the temperature sort of falls below or goes above a certain threshold. So it really doesn't think about what it did yesterday or what it did 2 weeks ago. It just works on a basic set of rules. Next is the model-based reflex agent. So this is a little bit more advanced, a version of the simple reactive agent. While it still relies on condition and, sort of the if-then sort of action rules to make decisions, it also incorporates an internal model of the world. So this model really helps the agent track the current state of the environment, understand how the past interactions might have impacted it. So this way it can actually make more informed decisions. So unlike, what we looked at earlier with the simple reactive agent, which just responds to some sort of an input, the model-based agents use the internal model to do a little bit of reasoning about the dynamics and make some decisions accordingly. So for instance, if you have a robot that's navigating a room, it might just not react to obstacles in its immediate path, but it also considers its previous moments and locations of the objects it has already passed. Next is the proactive cognitive agents. So these agents, they improve their performance over time by adapting to new experiences and data. So unlike some of the other agents we looked at earlier that rely on predefined rules or models, these agents continuously update their behavior based on feedback from the environment. This really helps them enhance their decision-making abilities and perform better in dynamic and uncertain situations. There are a few different components that make up these cognitive agents. So there's number one, the performance element. So this is where it's making decisions based on some type of a knowledge base, which is outside of maybe a language model that it might be using. Second is there's also a learning element, which helps it adjust and improves the agent's knowledge based on feedback and experience. Third, there's also a critic. So there's this component which evaluates the agent's actions and it provides feedback, either in the form of rewards or penalties. So if you've looked at reinforcement learning, it's a sort of similar concept that the critic uses where it, based on certain actions and outcomes, it'll either be a reward or a penalty for the model, so it can take that feedback and make correction the next time. The last one is really a problem generator, which suggests different actions to help the agent discover new strategies so it can improve its learning. The last one is really around specialized agents. And a specialized agent is an AI agent that's designed and trained for a specific narrow task or domain. Because their purpose is highly focused, they can be very efficient and accurate, but within that specific area of expertise. So that's really, when you look at some of the characteristics, they're generally single purpose. So these specialized agents will generally do one specific function. Maybe this could be performing some calculation or writing up a summary or maybe looking up data from a database. So they do something, they just do a very specialized task, but they do it really well. They generally tend to have domain expertise. So these agents are specialized, they're trained on data very specific to a domain. So this could be depending on the line of business, whether it's legal or finance or HR. These specialized agents are trained on that data. This is what makes them very highly efficient. So they are able to perform these special tasks much more faster and much more reliably than any sort of general purpose AI agent or even like a general large language model. The only downside to them is they do have limited scope. So if you give them a task that's outside of that domain, the results are either unpredictable or they can just make a lot of mistakes. So that's the only thing to keep in mind with specialized agents. On a related note, there's also, in the same category of specialized agents, you also do have orchestration agents. So an orchestration agent is really, you can think of it as a central coordination mechanism or like a master agent that manages and directs the flow of multiple specialized agents to achieve a bigger objective. So really this orchestration agent is responsible for things like delegation or task decomposition, synthesizing the results, and even sort of managing workflows and coordinating between the other specialized agents. And we'll have a chance to take a deeper dive when we look at some of the different modes and some of the design patterns you see with Agentic AI. So let's talk a little bit about robustness. I know that's sort of in the title for today's session, building robust Agentic AI systems. So when it comes to building robust Agentic AI, the robustness is not just about preventing failures. It does go beyond just preventing failures. It's really about graceful degradation and error recovery. So with a lot of these agentic AI technologies, but what I've seen is sometimes if you have an error happen at some stage in the pipeline or in the process, these can actually cascade, and sometimes they're hard to spot and even troubleshoot. So these are some of the challenges is, sort of being able to view the errors and sort of prevent them from propagating and having a cascading effect. The next is really around safety. So this is, given the fact that, these are, autonomous agents, safety is a concern, especially if you're in a regulated environment, in a regulated industry, or if there's high risk. So if you're dealing with patient data or healthcare or safety. When I say safety, I mean, things like manufacturing, or if you're dealing with aviation. These industries are regulated, and safety is a huge concern in many of these industries. So that is something to be mindful of. The other challenge is really around scaling. So these systems should be able to perform across different workloads, while most AI systems tend to leverage GPUs, since when it comes to agentic AI, they are primarily relying on GPU hardware for inferencing, which does put load under scale. So it's something you just have to be mindful of as you're designing these agentic systems. And lastly is around overall integration. In most real world use cases, the LLM is great for providing natural language and some of the things we love and like LLMs for. But in the real world, there's a lot of data that is outside of the LLM, and this data is either sitting in legacy databases, sometimes in file shares, unstructured data, in some cases maybe external APIs. So it's really that integration complexity of how your system would integrate with the rest of the environment is something you have to take into account to make sure your system is robust. In terms of the impact, so not having the right robustness. So you see some of the examples here on the slides where if you have a banking application that is maybe looking at certain transactions, so there's a lot of things can go bad where if someone's account needs to be credited, but it's actually getting debited, because the agent is doing something wrong. Or if you have a customer service agent that's working with customers to solve problems, it doesn't solve the problem, or it actually gives bad information to the customer, which you now have to deal with an angry customer. So these are some of the real world impacts when you have agentic systems that are not robust enough, or that have not passed some of the guardrails and some of the stress tests in the real world. So let's now talk about what are some of the core components we typically see with AI agents. So there's really 7 essential components, and we'll drill into each one of these. Depending on who you talk to, you may have some people mention more components, but these are really what I've found are the core components for agentic systems. Number 1 is perception and input handling. Next is planning and task decomposition. Third is memory, and then you have reasoning and decision making. You have action and tool calling, communication, and lastly, learning and adaptation. So we'll jump into each one of these and see what these components are and how they work together. So the first is perception and input handling. AI agents use perception to gather information about their environment through various input sources. So they then handle that input by processing it into a usable format, and they use that to recognize patterns, to understand the context, and then to inform their actions and achieve goals. So perception really is all about gathering that environmental data, and it's a fundamental process of sensing and interpreting data from the agent's surroundings. In terms of the input, typically, depending on the use case and what type of inputs your agent needs, it might end up being multimodal, where you may be processing text, you may be processing images, you might have to process, things like sensor data. And, these sensors could be either physical sensors, like cameras, LiDAR, microphones, IoT devices, or they could also be, like digital inputs, where maybe it's a database query, or it's some data coming back from an API, or maybe it's some user commands, is really what would, help the agent gather that input and then use that to sort of assess and learn more about the environment. Some examples here you see, for example, for chatbots, you basically use natural language processing, so when the chatbot responds, if there's a human on the other side, they can actually understand and interpret the response. With autonomous vehicles, a lot of the input is really things like camera data, LiDAR, and radar data. And then if you have, when you look at a lot of the integration in the enterprise, it's usually things like API, system logs, or user queries. So really, you can think of the perception and input handling more as a processing pipeline, where it starts off with data ingestion. There might be some cleaning and structuring of the data, and then in the end, what gets fed into the input handling for the agent would be that whole interpretation piece. Next is around planning and task decomposition. So when you look at, so we looked earlier at the reactive agents, which just use like a rule base, and they get an input and then they look at the input and then they sort of make a decision. When it comes to some of the more complex tasks, that logic is hard to apply. And that's where you start seeing a lot of these systems break down, because it's not a simple if then else statement. So this is where you're moving beyond the reactive responses, where now the agent, when it actually gets a problem or a goal, it has to start incorporating, it has to take that problem, break it down into smaller chunks. It has to sort of understand, how to manage dependencies. Are there tasks that could be sort of, do they have to be arranged in a certain way? Can certain tasks run in parallel? What are the different swim lanes, and how do I structure, break down, and execute these tasks? So a lot of the techniques really used with this are around logic-based planning, and of course using things like probabilistic models for any sort of uncertainty. In the real world, typical applications where you see this is a lot of the robotics. Actually, they use this. Any sort of AI-driven scheduling systems, and even things like if you're dealing with supply chain and logistics, a lot of that optimization does require this planning and task decomposition. Next, let's spend some time on memory. This is definitely, a key component. So memory in agentic AI gives the system the ability to store and recall past experiences. And the idea is to improve decision-making and overall performance. So we talked about earlier, with traditional AI, that processes each task independently. Agents with memory can retain context. They can recognize patterns over time and adapt based on past interactions. And this capability is essential for any goal-oriented AI application where feedback loops, knowledge bases, and adaptive learning are required. So memory is really a system that remembers something about previous interactions. AI agents don't necessarily need memory systems. So it depends on your use case. So if it's a simple reactive or a reflex agent, you really don't need any sort of memory. But if you have more complex use cases, where you need additional context, so this is where memory becomes very important. So in terms of types of agentic memory, a lot of the researchers, they categorize agentic memory very similarly the way psychologists categorize human memory. So you have both short-term and long-term memory. So short-term memory enables an AI agent to remember recent inputs for immediate decision-making. This type of memory is useful in conversational AI, where maintaining context across multiple exchanges is required. For example, if a chatbot that remembers previous messages within a session, it actually will give you much better responses when it has that additional context based on previous conversations. The long-term memory really allows agents to store and recall information across different sessions. So this actually helps them become more personalized, and it also helps them become more intelligent over time. So unlike short-term memory, long-term memory is really designed for more permanent storage. It's often implemented using databases or knowledge graphs or vector embeddings. So this type of memory is crucial for AI applications that require that historical knowledge. And if you want to build personalized assistance and recommendation systems, the long-term memory really becomes important. So one thing I do want to add is, in terms of implementing long-term memory, one of the techniques that is very popular is really based around retrieval augmented generation, or RAG. So this is something which really is a very useful technique for really providing that long-term memory for your agentic AI applications. So let's talk about reasoning and decision-making as our next component. So agent reasoning is the component that's actually handling the decision-making. It allows these agents to conduct tasks autonomously by applying conditional logic or heuristics, and then also relying on the inputs or the perception and memory, so it can actually pursue those goals that they've been given and optimize for the best outcome. So when you look at how these systems have evolved, the early systems were really rule-based, where if you had this basically almost like this if then else sort of logic. Then eventually we saw these systems, as problems got more complex,
they did need to have more reasoning. And there's a few different ways you could do some of this advanced reasoning. And this gets into some heavy duty math. When you look at things like Bayesian inference, it's basically a statistical method to determine probability of hypothesis. So if it basically starts off with a prior belief and combining it with data to quantify uncertainty. So it allows for degrees of belief rather than just true or false. Same thing with, when you look at, heuristics. AI agents can use heuristics for reasoning. So they're basically, for example, goal-based agents have a preset goal. And if they're using a search algorithm, they find sequences of actions that can help them achieve their goal and then plan these actions before conducting them. So that's really one of the paradigms. It's one of the basic paradigms, where you use heuristics or you use like a goal-based decision-making process. You move on next, as you need more. If you need something that's more sophisticated, if you have a more sophisticated use case, you would actually use the React, which is basically reasoning and action cycles, or reason plus act. So this reasoning paradigm involves a think, act, observe loop for step-by-step problem solving. And it's basically works in an iterative way to enhance the response. So the agent is instructed to generate traces of its reasoning process, much like what happens in a chain of thought reasoning in generative AI. So you'll see this if you use some of the reasoning models, and if you ask it a math problem or a PhD level question, you'll actually see the different steps that the model takes. And this is where you actually see it going, you see it going through the think, act, observe loop. So React does well on natural language specific tasks, and its traceability does improve, so you can actually see what that chain of thought is, but it can generate the same reasoning and actions repeatedly. So sometimes you'll see this go into a loop where it'll sort of have a set of thoughts and actions and observations, and then it gets stuck in a loop. So that's where ReWOO comes in, which is reasoning without observation. So unlike React, ReWOO removes the observation step and plans ahead instead. So the agentic, reasoning design, it really has three components. So it has a planner, it has a worker, and it has a solver. So the planner module breaks down a task into subtasks and allocates each of them to a worker module. The worker module then incorporates tools used to sort of execute each task. And then finally, the solver module will synthesize all the results from all these subtasks, and then it'll sort of come up to some sort of an inference or conclusion. So ReWOO generally tends to outperform React on certain NLP benchmarks. However, adding extra tools, it can sometimes degrade ReWOO's performance, and it doesn't necessarily do well in situations where it has limited context about its environment, because we've taken out that observation piece. Next, let's talk about action and tool calling. So this is where agents move from thinking to actually doing. So this is where you sort of go from, you've sort of gone through your reasoning, your chain of thought, and now it's time to actually execute. So this is really where you see and we'll have a chance to talk more about, tools and functions when we talk about MCP. But really, this is where your agent gets to either connect to external sources for information. Maybe it needs to look up a customer, so maybe it needs to do a database lookup to perform its task. In some cases, it might need to integrate with an API, so it needs to get data from another service. And so these are the digital interactions, and even these interactions can also be in the real world. Where if it's a robotics thing, where a robot actually has to move, is going to move to either perform some sort of an action or task. In terms of the tool calling mechanism, so really, this is where the LLM will get data that it's not trained on, and then it's going to, typically either ingest this data in JSON format, or even maybe output the data in JSON format if it's handing it off to a different agent. And then this is where, based on the actions, it would actually fall back into a reasoning process if it needs to, as part of being able to execute. Next, let's talk about communication. So AI agent communication really refers to how these agents interact with each other. So these agents could be interacting with a human being. They could be talking to another agent. So this could be agent-to-agent communications. Or this could also be a system integration. So an external system, for example, let's say if it's an API that the agent needs to interact with. In terms of, where this falls into the real world, some of the applications, typically would be, for example, customer service. So this is where if someone has a question or they have a question about a product or they have a concern, they would, talk to a customer service agent, and then the agent knows who the customer is, and what are maybe the history of the customer, what have they called about, what product they use, so it has the right context, so it can actually give them relevant information. And then agent really is around multi-agent systems, so this could be either knowledge sharing, this could be coordination, and then for system integration, it's really different workflows that could seamlessly integrate. Next, let's look at learning and adaptation. So learning enables agents to improve over time, and when you look at really the whole concept of continuous improvement. So that's really a mechanism these agents would use. And they really leverage on both the short-term memory and the long-term memory that we talked about earlier to be able to use some of that data and also the interaction with, whether it's with the human, with other agents, or even with the external systems to be able to have that continuous improvement. So if you sort of compare and contrast that with traditional ML uses more sort of pattern-based recognition. So it's not integrating with some of these external systems. It really doesn't have much context other than the data that it's been trained on. So this is where, using learning and adaptation, these agents actually get better over time and as they learn from doing more and from observing and pivoting. So really, without this sort of learning loop, AI systems become static and they really cannot adapt to new challenges, which is one of the reasons why you have this buzz around agentic AI, because that was one of the limitations with traditional machine learning. Now let's transition from components to design patterns. So we looked at some of the key components. There was like 7 components we talked about. There's really 6 broad design patterns. Now, again, depending on who you talk to, people may say there's maybe a couple of more, but really I picked these 6 because these seem to be the most common patterns that I have actually had a chance to see and work with. So let's look at each one of these. Let's double click into each one of these to as we look to architect and build some of these agentic systems. So the first is prompt chaining. So prompt chaining is also sometimes referred to as the pipeline pattern. It's basically a way to handle intricate tasks when leveraging LLMs. So rather than expecting the LLM to solve a complex problem in sort of a single monolithic step, prompt chaining, it uses like this divide and conquer strategy. The idea is to break down the original sort of bigger problem into a sequence of smaller, more manageable subproblems. And then each subproblem is sort of processed individually through a specially designed prompt. And then the output that's generated from one prompt is fed into the input for the subsequent prompt in the chain. So this sort of sequential technique, it actually brings in modularity. It also brings in better clarity with the interaction of the LLMs. So when you take a complex task and sort of break it down, decompose it, it just becomes easier to understand. And it's also easier to debug if you're having problems somewhere in that chain. So really each step in that chain, can be optimized so it can be very efficient in actually what it's processing in its step. So here's an example. So let's say if, we have, our task is to do market research analysis. So let's say we can pick an industry. Let's say this is on the real estate market, if you want to do an analysis. Now, if you're using the prompt chaining pattern, we can sort of break this down and you can, depending on your use case and what sort of data you're looking to get, you would solve this or you would break this down into different steps. But in this example, we're going to break it down into 3 steps. So really the first step is to summarize the findings. So basically what we want to do is we want to basically be able to craft a prompt where we can, and in this case, the LLM may have to leverage on external tools or an API, or maybe it's looking up a system maybe you're looking at a specific market, whether it's the Bay Area or New York or whatever the market is. So you want to basically have the agent summarize, have the LLM summarize the findings. Next, once the findings have been summarized, next what you want the agent to do is you want to actually draft a summary. So, maybe it's preparing an email. So maybe this is an email summary that you're going to be sending off to executives. So that's the second part of the prompt. So that input from the summary will actually go into the input from the findings will go into the executive summary. And then the last step is really from that summary, you want to look for trends, whether it's, what the pricing looks like, or what is the demand or supply, or what are the demographics that are moving into a specific neighborhood. So these might be different trends you might want to get from this data. So that's where that third step or the last step would be, is to identify, some of those maybe top 2-3 trends along with any supporting data. So this would be an example of how you would take a big problem, and in this case, we broke it down into 3 steps. Now, in your case, there may be more steps or there might be fewer. So it really depends on, what problem you're trying to solve and what are the outputs you're looking to or what are the outcomes you're looking to drive from that agent. Next is the routing pattern. So we looked at sequential processing before this, using prompt chaining. Now, that is a foundational technique or sort of linear workflows with LLMs, but it is limited in scenarios, requiring adaptive responses. So real-world agentic systems, they often face several choices that are determined by the state of the environment, the user input, or even the outcome of a previous operation. So routing introduces conditional logic into an agent's framework. So this lets it shift from a more fixed execution path to a model now where the agent can dynamically evaluate certain criteria and it can select from a set of possible actions. So this really makes it more flexible and more context aware when it comes to interacting with either the environment or the user. So let's say, for example, if you have an agent that was designed for customer inquiries, if it has a routing function, what it can do is, as soon as the query comes in, it can actually figure out the user's intent. In terms of what is the intention, or what is the crux of the query that is coming in. So based on this classification, it can then direct the query to a specialized agent, either for like direct question answer, or it can basically have a database retrieval tool for account information, or it can actually escalate to a human agent, like a human, for really solving this problem. So that's really where you are able to use the intent, and then you're able to route the query based on the intent. Now, there's a few different approaches in terms of how you can do this. The first is really LLM-based routing. So this is where the LLM itself can be prompted to analyze the input and output, and then it basically indicates what the next step is, or what the destination is. The other way you could do it is using embedding-based routing. So this is where the input can be converted into a vector embedding, and then this embedding is compared to embeddings representing different routes or capabilities. And then the query is routed to the route where the embedding is most similar. So this is sort of useful for semantic routing, where the decision is based on the meaning of an input rather than just keywords. Next is rule-based routing. So this really uses some predefined rules or logic. So this is almost like an if-then-else sort of logic, where you, based on certain keywords or patterns, you would make some decisions on where to sort of route the query. And lastly, you can use ML model based. So this is where the agent would use a model as a classifier, and maybe that model has been trained specifically on a small amount of data that is labeled just to handle this routing logic. So there's really 4 broad ways to actually implement this routing logic for your routing design pattern within your agent. Next is the parallelization pattern. So when it comes to a lot of these agentic workflows, we talked about where you take a big task and you break it down into smaller chunks. Now with a lot of these smaller tasks that they need to execute, in some cases you may have to do some of these sequentially, like how we did with prompt chaining, where the output from one prompt goes into the next one. But you may have tasks that could be done independently, or that could be done simultaneously. So this is where the parallelization pattern comes in, So this way you can leverage it for any tasks that are independent. So this would help you, do better in terms of performance. Your speed and execution will improve. It does require asynchronous execution frameworks, especially if you're going to call an API, and if while you're waiting for that API to process, you could have the agent do something else. So in this case, it may be able to execute multiple API calls, and then it could sort of, as different tasks complete, it can then put everything together and sort of put the pieces of the jigsaw puzzle back together. An example for this would be like a travel planning agent, where maybe the agent has a request to maybe book flights, hotels, maybe make restaurant reservations, and it can basically run these things off in parallel. So you could have the agent sort of kick off one workflow to check flights, another one to check hotels, and they could all be done independently. As the different tasks complete, it can then sort of put everything together and provide the summary back saying, here's a confirmation of all your bookings. Next is really the reflection pattern. So the reflection pattern involves an agent which is basically evaluating its own work. So this could either be an output that the agent provides, or it could be an internal state, and it's using that evaluation to improve its performance or to refine its response. So it's a form of self-correction or self-improvement that allows the agent to iteratively refine its output or adjust its approach based on feedback. So unlike a simple sequential chain where output is passed directly to the next step, or routing, which chooses a path, reflection introduces a feedback loop. The agent just doesn't produce an output. It examines the output or the process that generated it and identifies potential issues or areas for improvement, and uses those insights to generate a better version or to modify its future action. So this process involves a few different steps. So, first obviously is the execution step, where the agent performs a task or it generates some sort of an output. Next would be the evaluation or the critique of that output. So the agent, often would use an LLM call or another set of rules, would analyze the result from the previous step, and then the evaluation could check for either accuracy or style or completeness, or how well did it follow instructions that was given. Next would really be around reflection. So based on this critique or the feedback, the agent would then determine how to improve. So this might involve either generating a refined output, or maybe adjusting some parameters for the next step, or even modifying the overall plan that the agent came up with. And then this loop can be iterative, where it sort of goes through this evaluation and reflection and refinement process. And the reflection pattern really separates the process into two distinct roles. You have the producer and a critic. This is often called the generator critic or producer reviewer model, where a single agent can perform self-reflection using two agents, and this often yields more robust and unbiased results. So the producer agent is primarily responsible for performing the initial execution of the task. So it really focuses on generating the content or the output, whether this is writing code or drafting a blog post or creating a plan. So it takes that prompt and produces the first version of the output. Next, the critic agent. The purpose of this agent is to evaluate the output that's generated by the producer. So it is given a different set of instructions, often a distinct persona, where this critic agent could be, let's say you're a senior software engineer, you're a meticulous fact checker, and those instructions guide it to analyze the producer's work against specific criteria. So this could be maybe accuracy of the output, the quality of the code, or the tone of the voice used, or even the completeness and accuracy of the output. So it's really, the critic agent is designed to find flaws and suggest any improvements and provide structured feedback. This separation of concerns is powerful because it prevents the cognitive bias that an agent can have reviewing its own work. So the critic agent approaches the output with a fresh perspective, and it's really dedicated to finding any errors or areas of improvement And the feedback from the critic is then passed to the producer, which uses this to guide as it generates new and refined version of the output. So far, we've talked about agentic patterns that primarily involve orchestrating interactions between large language models, managing the flow of information within the agent's internal workflow, whether that's chaining, routing, parallelization. We talked about reflection. However, for agents to be truly useful and interact with the real world or external systems, they need the ability to use tools. The tool use pattern, often it's implemented through a mechanism called function calling, enables an agent to interact with external APIs or databases or services or even execute code. It allows the LLM at the core of the agent to decide when and how to use specific functions based on the request or based on the current state of the task. So there's a few different pieces to this process, as you can see on the slide here. So the first is the tool definition. So this is really where the external functions or capabilities are defined and they're described to the LLM. And the description includes the function's purpose, its name, the parameters that it accepts, along with the types and descriptions. Next is the LLM decision. The LLM receives the user's request and the available tool definitions. And based on its understanding of the request of the tools, the LLM decides if calling one or more tools is necessary to fulfill the request. Next is function call generation. If the LLM decides to use a tool, it generates a structured output. Generally, it's like a JSON object that defines the name of the tool to call and the arguments that have to be passed to the tool. So this is extracted from the user's request. Next is tool execution. The agentic framework or the orchestration layer will intercept this structured output. It identifies the request tool, and then it executes the actual function with the provided arguments. Last is really the observation or the result. So this is where the output from the tool and the tool execution is returned back to the agent. This pattern is fundamental because it breaks down the limitations of the LLM's training data and allows it to access up-to-date information. It can do things like perform calculations that it wouldn't normally be able to do. LLMs still struggle with math sometimes, where which they are getting better now, but they sometimes do struggle with some basic things that how many R's are in strawberry. That has gotten better, but then you can rely on some of these tools to do some of those specific calculations. So you have frameworks like LangChain or LangGraph or even CrewAI and many others that provide support for defining tools and also integrating them into agent workflows, often leveraging the native function calling capabilities that LLMs have. While a monolithic agent architecture can be effective, especially for well-defined problems, its capabilities are often constrained when faced with complex multi-domain tasks. The multi-agent collaboration pattern that you see on this slide really addresses some of these limitations by structuring a system with a set of specialized agents. So this approach is based on the whole idea of task decomposition, which we discussed earlier, where a high-level objective is broken down into discrete, smaller tasks, and then each subtask is assigned to an agent that's equipped with specific tools and then reasoning capabilities best suited for that task. For example, a complex research query might be decomposed and assigned to a research agent for information retrieval, and then a data analysis agent can basically do statistical processing, and then a synthesis agent can create that final report. So this distributed architecture, it does give a lot of advantages, including better modularity, better scalability, increased robustness. So this way, if there's a failure in one agent, it necessarily doesn't cause a complete, like a total system failure. So this collaboration allows for, good synergies and outcomes where collective performance of the multi-agent system will go beyond what a single agent can deliver. In terms of, how these multi-agents collaborate, there's a few different ways in which this collaboration happens. There are, in some cases, sequential handoffs, where if you have either tightly coupled tasks or if you have strongly dependent tasks where the output from one task is important for the input to another. For example, if the task is, hey, book my flight only if I can get availability in this hotel. So then, there's this some sort of a handoff, for those specific dates, say, for example. So this is where you would sort of move into that pipeline stage where we looked at the pipeline planning pattern. And then if you have parallel processing, multiple agents can work on different parts of the problem simultaneously, and then, their results can be combined. There is also the debate and consensus. So this is where in multi-agent collaboration, where if you have agents that have different perspectives or different information, they sort of can engage and they can almost discuss and evaluate options and reach some sort of a consensus, and then make a final decision on what that output or what that decision needs to be. You also have the hierarchical structure. So this is where you could have like a master or a manager agent that can delegate tasks to worker agents, and really based on and give them specific tools that they need. So from a security perspective, if it's a researcher agent, maybe they only need to search either the internet or a specific system. So the manager agent only assigns tools that specific agents need. You could also have maybe expert teams. You could build an expert team where you have agents with specialized knowledge in different domains that can collaborate and produce complex output. And then you also have the critic reviewer pattern we looked at, where agents will create, things like, maybe a plan or a draft, or will answer a question. And then a second group of agents will sort of review and critique, assess, and provide feedback. So this really, this sort of multi-agent collaboration gives better robustness, better quality, and there's a reduced likelihood of hallucinations and errors when you use this sort of multi-agent collaboration. Understanding the different ways in which agents can interact and communicate is really fundamental to designing effective multi-agent systems. So really, there's a few different architecture models, if you will, and each has its own sort of unique advantages and challenges. At the most basic level, what you see towards the bottom of the slide, that's really the single agent is sort of the most basic agent. It operates autonomously, without much direct interaction or communication with other entities. It's sort of off in its own little world, doesn't have a lot of dependencies. Now, these are the easiest to implement because there's no external dependencies, and really its capabilities are limited by the individual agent's scope and resources. It is suitable for tasks that are decomposable into maybe smaller problems, but each is solvable by that same agent. Next is really the network model. So this represents an important step towards collaboration where multiple agents interact directly with each other in a decentralized fashion. And communication typically occurs peer-to-peer, allowing for sharing of information, resources, and even tasks. This model really fosters better resilience because the failure of one agent doesn't necessarily cripple the entire system. However, managing communication overhead and ensuring proper decision-making in a large unstructured network can be challenging. So the supervisor model, here you have a dedicated agent acting as a supervisor or as a manager. And this agent is overseeing and coordinating the activities of all the sort of subordinate agents, if you will. And then the supervisor acts as that central hub for communication, for task allocation, for conflict resolution. And this hierarchical structure offers clear lines of authority. And this can actually simplify management and control. But it does introduce a single point of failure where the supervisor can become a bottleneck if it gets overwhelmed by a large number of subordinates or complex tasks. In the hierarchical model, it expands on the supervisor concept to create a multi-layered org structure. So this can potentially help remove some of those bottlenecks where if you have a single supervisor where it's coordinating everything, by setting up this hierarchy, you've introduced a few more layers. So you have multiple levels of supervisors, and then you have higher level supervisors overseeing, lower level supervisors, and ultimately it's a collection of agents at that lowest tier. This structure is well suited for complex problems that can be decomposed into smaller sub problems, and each managed by a layer of specific layer within the hierarchy. So gives you a very structured approach to solve some of those tough problems. And the custom model really is where you have the most flexibility. So this really allows for the creation of different structures, different relationships. So you could sort of use it's almost a blend. It could be a blend of some of the other models you see here on this slide. So in summary, really the choice of the interrelationship and communication model for a multi-agent system is critical. It is a critical design decision, And each of these models you see here, it does have some advantages and disadvantages. And really the optimal choice would depend on things like, what is the complexity of the task? What is the number of agents you have? What is the desired level of autonomy you need in your system? And that's really what would help you drive some of the choices you would make here. So let's talk. I know we've talked a lot about, agents requiring to connect to external sources and external tools. And this is really where MCP comes into play. So Model Context Protocol, or MCP, it's an open standard that was developed by Anthropic. And this was really the idea behind MCP was for giving the ability for AI models or LLMs to connect to external data sources and tools. So you can almost think of MCP as it's almost like a standard interface. You can think of it as maybe like a USB-C adapter, which once you have a USB-C adapter, you can actually connect your device to any sort of standard. Wherever you have a standard USB-C port, you can just plug it in and everything just works. So that's really the idea behind MCPs, allowing standard protocols to actually communicate with some of these different tools. Now, it does use a client-server architecture. So where you basically have, in this case, the client would be the AI application. So let's say this is your agent, which is the client. It's going to use MCP as a protocol, which is an open protocol that would connect to, let's say, a server. Now, the server could be a tool. So this could be, maybe an interface that the tool would use to translate the AI's requests into actions on various services. So this could be maybe a database or an API. So this standardization simplifies integration, and it allows AI agents to dynamically discover and interact with various capabilities without having to build custom integrations for each tool. So this way it just gives you a standard framework that you can actually very easily reuse. So the way it really works is you basically have an MCP host, which is in this case would be your AI application, that would actually initiate a connection to an MCP server. Then the host basically goes through a discovery where it's going to query the server to discover what tools and resources are available on this MCP server. And this really is where it helps enrich the model's context, with the relevant information from those connected servers. And then based on the task, the agent can actually pick the right tool and then basically execute them using this MCP server. In terms of implementation, MCP is powerful, but it does require some careful implementation. Obviously, in terms of security, you definitely want to make sure you are exposing the right tools to the right agents, and making sure even from a data, providing least privilege to only giving the data the tool needs access to, and not exposing more data than what it actually needs. Being able to handle errors, and then also not only handle errors, recover once there's an issue. From a design standpoint, really having agent-friendly APIs. So for instance, if you have an MCP server that connects to your backend database, where your agent can basically ask a question, hey, show me all the customers that have bought product X, or that have spent X amount of dollars in certain time frames. So you really want those APIs to be agent friendly, and also having the ability to interpret the data that comes back from the server would actually give you better deterministic features. So this way you're not getting different responses from your MCP server, especially if it's data you expect to be consistent each time you ask the MCP server for. With that, let's actually switch and take a look at a live demo. So let me actually fire things up and switch to a demo here. Okay. So what you're looking at right now, and maybe I'll try to make this a little bigger here, hide that. So this is really, since we're talking, we're talking IK, and I know we're talking about, how you can land that next opportunity. So what I actually built here is actually a simple agentic AI job finder. And in terms of what it can actually do, so some of the features, so it can do, things like a standard search, where it'll sort of, based on the criteria you give it, It'll go off, do a search and come back with an analysis. You could also sort of turn a few knobs if you are wanted to focus on a specific salary range or a specific company, or maybe even a specific type of role, maybe just find entry-level roles or internships. It can actually do that. In terms of some of the agents that this program uses, so it does have a job search agent. So this is where, there's a few different there's a few different things that the agent does. So it can sort of research and it can do a lot of searching. There's a company-specific targeted agent. So it can, sort of look at specific companies, and then based on some of the capabilities, we have a few different agents here. So there's an analysis agent. There's also a message writer agent, so it can actually create, it can write emails and it can create like a LinkedIn post for you as well. So you can really have it do some custom things and create some content relevant to your job search. From a tooling standpoint, there's, a few different tools which we covered in the features as well. So you see that reflected in the tools here. So you do have a search tool. Of course, you have tools based on salary or company. And then also there's, tools for you to read documentation, and then also to be able to create the output summary or output files, which has all the results. So I have some prereqs here. In terms of what it's actually using, it is actually doing a Google search to look for jobs. And it is using the Serper API, and you can actually get a free key. I mean, they have some, they have a fairly decent free tier, so you can actually just get an API key from Serper. I am using Gemini in this case as my LLM, but if you wanted to use a different LLM, you might have to make a little bit of a code change, where you update the code to use, if you want to use OpenAI or something else. But this demo is actually built using Gemini. You can actually find the Git repo. So this is a public repo. You see the link here. So you can actually clone this repo and then basically do a few things in terms of your setup. So you would set up your Serper key, your Gemini key. You would also tell it the model that you're using. So let me actually quickly move to the code so I can actually show you the demo. So let me actually come in here quickly. A few things. So what we're right now looking at is the README file. I just want to quickly show you the config file. So this is, maybe you can make this a little bigger. So this is really the file that the system would use to actually do your job search. So in this job config area, you actually want to put in maybe the title of the job you're looking for. So in this case, let's say it's software engineer. To give you better search results, you don't want to add any variations to the title. So I actually, some people may call it developer or full stack or backend. So I sort of added a bunch of some of these alternate titles. So this way you get better. You want to broaden your search. So you could narrow this, based on what actually comes out when you run this agent. There's things like experience and skill level, and then there's also required skills. So these are, so if you have a background, let's say in Python and JavaScript and React, and you want to make sure you find a job that sort of hits your strong areas, you can include that. If there's other things that are nice to have, you can include those as well. There's location preferences, salary, and then there's a few other things here if you want to actually target this. So these would actually kick in when you do the targeted search. But hopefully you get the idea. The key things really is going to be around your job config data, your title, experience, and skills. I would really look at those areas. In terms of how do you really run this, you can basically just run Python run search, which is what I'll do right now. So let me actually get rid of this. So we have the full screen. I can make this a little bigger. I've already cloned the repo, and what I'm going to do is I'm going to run Python run search. And what it actually gives you is it actually gives you a menu here. And there's a few different options in terms of how you can search. To keep this demo, I mean, some of these, depending on what type of search you run, it can take a while to run. So to make this demo simple, I will actually go with the quick search option. So what it'll do is it'll do a fast search with minimal filtering, and you'll get to sort of see some of the steps the agent takes. So I'm going to just pick 5. I'm going to let it go. And you'll see the first thing that it actually does, as it sort of does this search, is I am using CrewAI as the framework here. So you'll see, the first thing you see here is the execution has started. It sort of gives you a job ID of what's running. And then the first task is really for the senior job researcher agent. And you'll actually see the task here is to perform a quick search. So in this case, it's getting this data from the config file. And you'll see some of the keywords I had was, software engineer remote. I had a location as, the Bay Area. And then this was really what the task was, to provide a quick overview of opportunities with minimal filtering, and then focus. So you can really tweak this task based on your requirement. And you'll then see the next task that it's doing is, it's sort of, you can see this sort of chain of thought reasoning going on here. So it's saying it wants to do a search. And, since we chose this quick search option, it's actually using the quick search tool. In this case, the quick search tool only has access to the Serper API to do that search. So it actually does put in those keywords. It uses the tool, it plugs in those keywords, and then you'll see from the tool, in this case, the Serper API, it actually returned these results. And in this case, I think it came back with 10 results. And you'll see it actually puts in the links. And if you scroll back down here, the next thing is you're going to have the job researcher sort of pass through the results, and they're, doing a little bit more filtering and analysis on the results. So you see that piece coming here. So we have a few hits to our search coming back here, which you see. So I'm going to sort of go down here. So in this case, it's giving you some notes as well. And, so the first agent in this case has actually completed their task. And now it's actually, you'll see the execution is complete. From a Crew standpoint, we did the simple search, so it didn't go through multiple steps. And then you actually see the results here shown as the output with the search. And then it sort of gives you this message, is done, search completed. And it's actually telling you to check because it drops the output into the job post directory. So if you actually go back here, and if I look at the job post directory, you'll see I have the quick search results. So if I were to get rid of that, and if you actually look at the quick search results, you'll actually see the actual results here. I'm not sure why it's showing up in a different language here or Arabic, but this is really what's coming back from the tool. So this is not the agent doing anything. It's the tool running the search, and it looks like they're posting it in a different language for a couple of these, but it actually tells you the title, it tells you, like the company, and we see here staff software, yeah, that's Sophie. So it actually arranges that, and it gives you a link as well if you want to click in and see more information about it. But that was really the quick demo. I would encourage you to clone the repository. There's other things you can do with this. There's more fancy searching and more additional handoff and analysis, and even things like email writing. So do check it out. But for the purposes of this demo, I will leave it here, and let's get back to the slides so we can actually wrap up for today. Okay, so in terms of really just to wrap this session up, if you're really looking to build robust agent systems, number one, start with the core components. So you want to define the perception and reasoning requirements in terms of what your agent or what your agentic system needs to do. You do want to make sure you design the right memory and communication architecture. So if you need to use like a RAG-based architecture, or if you need short-term memory, and even depending on the communication architecture, how do your agents need to communicate? Do you want to use a hierarchy? Do you want to use a manager? Do you look at the different ways in which they would collaborate? So you want to establish that. Next, you do want to apply the design patterns. So we looked at, like 6 different types of design patterns. So you want to use, if it's complex workflows, use chaining. If you want to use routing, you can actually even mix and match a lot of these design patterns based on what exactly you need. If you want to get better performance, look at what tasks or workflows you can parallelize. So you want to parallelize those. And then if you want to improve the accuracy and even the quality, you definitely want to add reflection, into your system. Last, you do want to integrate any sort of tools that you need. So you want to define the tool interfaces. You want to avoid building any sort of point-to-point connection. So you use MCP. It's almost turned into the de facto industry standard for having your agents, use tools. So you definitely want to consider MCP. And then also, you want to figure out how do you want to do the coordination between multiple agents. So to sort of wrap this up in summary, to really get to building robust agentic systems, you want to start with a component architecture. So we looked at we looked at 7 components that actually provide that foundation. From a design pattern standpoint, we looked at 6 design patterns. So they actually address things like complexity, performance, even the quality. You want to use a systematic approach. So you want to combine the components and the patterns thoughtfully. So, really understand your use case. You see what is the problem you want to solve, what's the most effective way to solve the problem, and then using the components and architectures you've looked at, you want to apply those. You want to try to use standardization. So, using things like, MCP, give you a scalable and repeatable and well-designed system. And then in terms of robustness, you want to think about how you handle errors, how do you handle things like security and graceful degradation when things fail will be very critical for you to build those robust systems. So the future of AI is agentic, and I'm hoping these tools would help you build them reliably. With that, I wanted to say thank you very much, and hopefully you can take this to design and build your next agentic AI system.
If you like this video, you will love what I have to say next. The 14-week Agentic AI program at Interview Kickstart helps engineers build real career-ready skills. You'll work on 2 live projects with FANG instructors and leave with portfolio work that actually makes a difference in hiring. Over 20,000 tech professionals have already trained with Interview Kickstart, with many moving into roles paying upwards of $300,000. Want to learn more? Join the free upcoming webinar, ask questions, meet the instructors, and see if it's a fit. Not ready yet? No problem. Start with the Agentic AI building videos here on the YouTube channel. We recommend this one. Either way, the key is to just get started.